So alright, so now we want to minimize the KL divergence between these two, right? So I choose Q of Z so that it approximates PZ given X. Yeah? So we want to minimize the KL so that these two are as close as possible to each other. So we have the KL divergence of, in our case, Q of Z, yeah, and the probability of Z given X. Alright? And that is equal to, we know it's a sum, yeah, and the sum of Q of Z times the log of Q of Z divided by this one here, probability of Z given X. Alright, so what we're going to do now is we're going to flip and put a minus here, minus the sum of Q of Z, the log of PZ given X divided by QZ. Alright, now PZ given X is this one, right? So we're going to use base rule equals minus the sum Q of Z log of Px given Z times Pz, yeah, divided by Px. Yeah, so that's this one, and then I still have the Q of Z here. Alright, now this Px given Z I'm going to replace by this one, so is minus the sum of Q of Z, and then we have the log of Pxz, that's the joint, divided by Pz, and then I'm gonna keep all this, so Pz divided by Px 1 over Qz, yeah, and this is the log of this whole thing. Alright, so you can see that these two disappear. Yeah, so we have minus the sum of Q of Z log Pxz, which is your joint, divided by Q of Z times 1 P of X. Alright, so now we're gonna calculate this. The log of a product is the sum of the logs. Yeah, so equals minus the sum Q of Z, yeah, times the log of the joint divided by Q of Z plus the log of 1 divided by P of X. Alright, so that equals minus the sum of Q of Z times the log of Pxz divided by Q over Z. Yeah, and then you have minus, but I want to swap this, so again it's going to be plus the log, plus the sum of Q of Z times the log of P of X. Yeah, and this log of P of X does not depend on Z, and basically here we sum over Z. Yeah, so that means that I'm gonna have my KL divergence of Q of Z and the probability of Z given X equals, yeah, we have this one here minus the sum over Z of QZ times the log of the joint probability of X and Z divided by QZ. Yeah, and then I have plus the log of Px times the sum over z of qz. And the sum over z of qz is nothing more than 1. So basically what we want to do is we want to minimize this one. Because if we minimize, these two distributions are similar, right? But here you have a negative sign, so let's call this quantity L. Yeah? And log of px is a constant. This is a constant. Does not depend on z. Yeah. So if we want to minimize this, that means that we want to maximize L. Alright, so we want to maximize L. And let me now reshuffle this a little bit. We have the log of P of x equal to this one, the KL, plus L. Right? Because I bring this to the other side. KL is positive, we know. Yeah? So that means that log P of x is going to be larger than L because I'm going to add something positive to L. Right? So that means that L is smaller than log P of x. Right? So if I maximize L, that means I maximize the log of P of x. But that means that you maximize P of x. All right, and that's exactly what we want. So L is called the variational lower bound. All right. So if you maximize the lower bound, if this is the lower bound of your function, you maximize this, you also maximize your function. Yeah. So we want to maximize the variational lower bound. So now we have our lower bound, a variational lower bound for the log of P of x. All right. And what is this L? Well, L equals the sum over z of qz times the log over pxz. This is your joint distribution divided by qz. Alright, now let's replace the joint with this one times this one, so that equals the sum over z of qz times the log of px given z times pz, and that is this one, and then divided by qz. So now we're gonna change this one, so equals the sum over z qz times the log of let us take these two together, px given z divided by qz, yeah, and then plus qz times the log of pz. Now let us So let us do PZ here. Yeah, and what I'm gonna do is I'm gonna put this QZ together with the PZ, right? So I'm gonna take this one out here and I'm gonna put it here. All right. Now, if we look at, let me just put the brackets here. Yeah. If we look at this term here, yeah, then this is, if I swap these, there comes a minus here, so that is minus the KL value of Q and P, right? And because this sum goes here as well, yeah? And then here, this one is basically the expected value. This is the expected reconstruction loss with respect to Q of Z. Yeah. So it is, in this case, this is equal to the expected value with respect to QZ of, so that sum gives you the expected value of log probability of X given Z, right? So that is basically your expected reconstruction loss, and this gives how close Q and P are together. Yeah? So as a final formula, the lower bound equals the expected value over QZ of the log of the probability X given Z. Yeah, that's the reconstruction loss, right? Minus KL of Q of Z and P. Yeah, and in our case, this is P of Z, right? So Q of Z should actually be as close as possible to P of Z. Now remember, P of Z is a prior. All right, so this is the value for L, and we want to maximize. We want to maximize.